Imagine a perfectly sealed box. If you pump out all the air, block out all the light, and remove every single atom of matter, common sense says you are left with absolutely nothing, a true vacuum, a state of zero energy. For a long time, physicists agreed. But in the 1960s, that classical idea hit a wall. Scientists had built highly accurate mathematical models to describe the fundamental forces of the universe. They worked with incredible precision, except for one specific, fatal flaw. The math insisted that the tiny building blocks carrying these forces must have exactly zero mass. But physical experiments proved the opposite. Those particles were undeniably heavy. This wasn't a minor error. If those particles actually lacked mass, atoms could never form. Without atoms, you have no stars, no planets, and no life. To fix the math without ignoring reality, a few theorists in 1964 proposed a radical hypothesis. They suggested that the lowest possible energy state of the universe, that perfectly sealed, empty box, isn't actually empty. It was a necessary shift in perspective. If these particles had mass, then even the emptiest parts of the universe had to contain a hidden, universe-spanning presence. We now call that presence the Higgs Field. To understand how it functions, imagine a universe modeled after a children's ball pool. If this pool has high, opaque walls, and you are standing on the outside, you can't see what's inside. A scientist looking at it from a distance might conclude the space is completely empty, mirroring how the background vacuum of space appears to us. But drop a particle into that space, and reality changes. Moving through the vacuum is like wading through plastic spheres. The field pushes back, and this physical resistance determines mass. A top quark drags heavily, while an electron slips through easily. Mass is merely a cosmic interaction. It is a physical byproduct of moving through the background of the universe. If the Higgs field is completely invisible and exists uniformly everywhere, we face a major hurdle. How do we actually prove it is there? Detecting something that exists everywhere is notoriously difficult, but our ball pool model suggests a way to force a reaction. You have to disturb the baseline state. If you jump hard enough into the pool, the impact transfers energy into the system. For a fraction of a second, a single ball erupts upward, becoming visible above the walls before falling back down. That brief, visible splash is the Higgs boson. It is a localized quantum excitation of the underlying field. Physicists don't look directly for the invisible field. They hunt for that unstable, fast-decaying boson, because its temporary presence proves the field is hiding right below the surface. To create a splash large enough to observe, humanity built the Large Hadron Collider at CERN. The collider uses brute force. It accelerates protons to 99.99% the speed of light, colliding them head-on to inject energy levels never before achieved in a laboratory directly into the vacuum. In 2012, after a 40-year search, the ATLAS and CMS experiments finally captured the decay signature of the exact splash they were looking for. This chart shows the collision data. Amidst all the background noise, a distinct spike emerges exactly at an energy mass of roughly 125 giga-electron-volts, or GeV. The particle producing this spike had zero spin and even parity, the precise physical properties required to be a Higgs boson. That specific data spike completed the standard model of particle physics and earned the original theoretical founders the 2013 Nobel Prize. By finding this fleeting particle, we proved that what we once thought was empty space isn't empty at all. The darkest, quietest corners of the vacuum are actually buzzing with the invisible machinery that gives our entire universe its physical substance.